And welcome to the section 8.1 lecture video on the distribution of the sample mean. The probability distribution of a statistic is a probability distribution for all possible values of a statistic computed from a sample of size n. The probability distribution of the sample mean x bar is the probability distribution for all possible values of a random variable x bar computed from a sample of size n from a population with a mean of mu and a standard deviation of sigma. Suppose that a simple random sample of size n is drawn from a large population with a mean mu and a standard deviation sigma. The sample distribution of x bar will have mean of mu sub x bar equals mu and standard deviation of sigma sub x bar equals sigma divided by the square root of n. The standard deviation of a sample distribution of x bar, sigma x bar, is called the standard error. So basically the idea here is that the larger your samples are, the closer this distribution gets to the mean. So the smaller your standard deviation gets. So if you have a very large sample, the chances are that they're not going to deviate from the means of those samples are not going to deviate very much from the sample mean. However, if you have a small sample, those could deviate quite significantly from the population mean, the means of those samples. But in general, if you took all the means of all the samples of a certain sample size and you took their average, if you found their mean, then what you would get is the same thing as the population mean. So mu sub x bar, if I took all the samples of size 49 from my population, mu sub x bar is going to be exactly the same as mu for the population. So the mean of all those means would be exactly the same as the sample mean. And the standard deviation, sigma sub x bar, is going to be the standard deviation of the population divided by the square root of n. So in this case, that would be 14 over 7, which is 2. Okay, and that's simply how this works. So, for example, this second one here, since mu is 27, mu sub x bar will also be 27. And since sigma is 6, n is going to be sigma sub x bar is going to be 6 divided by the square root of 15, which is 6 divided by the square root of 15 is 1.549. So we could do a quick example of this by hand. So let's say we had the data set. So let's say our data was 1, 3, 7, and 19. Let's actually not do 19. Let's do 13. Okay, so what we could do real quick is using our calculator, I could find the mean. So let's call this my population. Okay, and so if we did, our population mean is just going to be adding these all together and dividing by 4. So 1 plus 3 plus 7 plus 13 is 24. Divided by 4 is 6. And then we can do our standard deviation, which I'm going to use the calculator for. So if I go to my class calc app and we go to the graphing calculator and we go to statistics, we can do the standard deviation. of 1, comma 3, comma 7, comma 13. Okay, and I get sigma of 4.583. Okay, 4.583. So the idea here is if that's my population, what I want to do is I want to take all the samples of, say, size 3. Okay, so we can take all the samples of size 3. So these are all my different samples. Okay, so I could have 1, 3, and 7. I could have 1, 3, and 13. And I could have 3, 7, and 13. Actually, I forgot one. I could have 1, 7, 1, 7, and 13, and I could have 3, 7, and 13. Okay, so the idea of the sample distribution of the mean is now I find the mean of each one of these. Okay, so I find the sample of each one of these. So we would find the mean for each one of these. So 1 plus 3 plus is 11 halves, so 5.5 would be the mean for this first one. The mean for the second one is 1 plus 3, that's 17 halves, so that's 8.5. And then the next one is 21 divided by 3, which is 7. Oh, I'm doing these wrong. These aren't right because I'm dividing by the wrong number. Sorry. 1 plus 3 plus 7 is 11 divided by 3 would be 11 thirds. 3 plus, that's 17 thirds. This one still is 7. And the last one would be 23 thirds. So the idea behind mu sub x is I find the mean of my mean. So mu sub x bar would be 11 thirds plus 17 thirds plus 7 plus 23 over 3 divided by 4 because I have 4 inputs. And mu sub x bar is, let's see, 11 plus 17 is 28 plus is 51. 51 divided by 3 is 27. So 27 plus 7 divided by 4. Oh, wait, 17 plus 7 divided by 4, not. So is, when you add those all up, you get 24 divided by 4, which is 6. So notice we got exactly the same value here and here. So mu sub x and mu sub x bar are exactly the same. And sigma sub x bar should be sigma divided by n, the square root of n. So it should be 4.583 divided by the square root of 3. And so we could do that. 4.583 divided by 3, the square root of 3, is 2.646. And we could check and see if we get the same thing if we use our calculator to do the standard deviation of our 4 means. So if I go back into my class calc app here, and I put in my means, they were 11 divided by 3, comma, 17 divided by 3, okay, so now notice we did not get what we would expect because I got sigma is 1.528. So sigma sub x bar was 1.528. 0.28. Now, that's really important. So this works for the mean no matter what. But notice a really important phrase from up here in the definition, which is from a large population. Was this a large population? No. So we shouldn't expect the sigma to work. But this is the idea behind how sample distributions work. What you're doing. You have a population, you pick out all the samples of a certain size, you find their means, and then you find the mean of those means. And that mean should match the population mean, and the standard deviation is going to be smaller than the original standard deviation. And with very large populations, whether you get it from the data or you use this formula, you should get the same answer. But the real key is that as you find the mean of the means, the data gets clumped in closer and closer together. So, what can we do with this? Well, the most important thing we're going to do with this is we're going to use it to find probabilities of means occurring. So let's talk about that. So first of all, the shape of a sampling distribution x bar, if x is normal, if a random variable x is normally distributed, the distribution of the sample mean is normally distributed. So that's one really important thing. So if your random variable is normally distributed, so is the sample mean. So that's step one. If you have normal data, you can always do this stuff. The central limit theorem, though, allows us to take this even further and say that regardless of the shape of the underlying population, so no matter how skewed it is, the sampling distribution of x bar will become approximately normal as the sample of size n increases. So that's the central limit theorem. We assume that the distribution of the sample mean is approximately normal when n is greater than or equal to 30. So we use 30 as that bar for the sample size to guarantee that our population will be approximately normal. Because if we have approximately normal data, then we can use it to calculate probabilities, which will be very useful when it comes to doing inferential statistics. So what must be true regarding the distribution of the population in order to use the normal model to compute the probabilities involving the sample mean? So in this case, we have a simple random sample of size n equals 12 is obtained from a population with mu equals 64 and sigma equals 77. So for that to be the case, for us to be able to, what has to be true about this population? Well, because n is less than 30, we have to have the first thing up here at the top of the page happen. The population, the samples, are taken from must be normally distributed. So assuming that's the case, then we can describe it. And the way we can describe it is if the population was normal, then the sample distribution of the mean is normal with mu sub x bar equal to 64, the same as the mean, and sigma sub x bar equal to 17 divided by the square root of 12. And then we could write that out as a decimal if we wanted to. So what this is useful for now is we can find normal distribution. So if our data was normal, then this distribution would have to be normal, and we can show what that looks like, right? So we can use our graphing calculator app, and we can draw a normal distribution with the mean and standard deviation we just said. So we can hit stat, distribution and plot, normal distribution, and we can put in our mean of 64 and our standard deviation of 17 divided by the square root of 12. Okay, and then we should be able to see the normal distribution, and there it is. That looks like that. Okay, and now that we've got the normal distribution, we can do some calculations with it, right? So we can, if I wanted to know what's the probability that x bar is less than 67.3, what's the probability that a mean would be less than 67.3, I can use my CDF just like in the last chapter, and I just put in 67.3, and we can see that the probability of that is 0.7493. So this would be 0.7493. We could find the probability that x bar is greater than or equal to 65.2. So we just we want to be bigger than 65. We want to be bigger than 65.2. So that means x 65.2 is less than x, and the probability of that would be 0.403. And then it says, answer the above questions using n equal to 20. What happens to the probabilities as the sample size is increased? So if we do that, here actually is the graph when it's 12. So let's stick with that for a second. So there's our graph when it's 12. Let's do the same thing. Let me draw it again. Let's draw another one. So now I can do normal distribution. The mean stays the same. The standard deviation of the population stays the same, but the distribution standard deviation becomes this over the square root of 20. And so you can see what happened here by changing the standard deviation to the square root of 20. The population, the standard deviation got smaller, so the graph got shrunk in towards the middle. So it got taller. And let me actually change this color so that it's a little easier to see. The graph got taller and got the standard deviation got pulled in. So when I try to do the same CDFs that I did on the other one for this one, so here let's just do both of the, see if I can do both at the same time. So the first one was x is less than 67.2. And this one's, so we'll put the 67.2 in here too. Notice that they start in exactly the same place. But the probability of the second one is higher, 0.8001, because the graph is taller. So more of the data gets sucked into that area. But they start at the same data point. So because the mean is in the middle, when we did the probability that x bar is less than 67.3, I actually put in 67.2, it occurs to me, I think. So I need to change that to get the right answer. But if I put in, I get 0.8073. So when the mean is part of the probability you're finding, if your n goes up, the probabilities get higher. However, if we change it to now x is greater than 65.2, so we can put those in, so 65.2. So let me put it into both. So you can see that they start, 0.2. They start from the same place again. Now this time the answer for the second one is smaller because the mean is not included. Okay, so the mean is not included for that second one, so the answer is smaller. So there's actually less area out in the tails than there was before. So this answer was, 0.3761. So the probability that x bar was greater than or equal to 65.2 was 0.3761. So as the sample size goes up, probabilities that include the mean increase, probabilities that do not include the mean decrease. And so we can do some applications with these. So the famous geyser, the most famous geyser in the world, Old Faithful in Yellowstone National Park, has a mean time between eruptions of 85 minutes. If the interval of time between eruptions is normally distributed with standard deviation of 21.25, answer the following questions. So what is the probability that a randomly selected time interval between eruptions is longer than 95 minutes? So notice we're looking at a randomly selected time interval. So that's one data point. So to do that one, we set up our normal curve the same way we have before. Okay, so we'll put in our data values here, hopefully. So our mean is 85 and our standard deviation is 21.25. So 85, comma, 21.25. And we can zoom in on that, hopefully. Okay, and so there's our normal distribution. And let's clear out our interval that we'll do. So there's our normal distribution. Notice I didn't divide by 21 by anything yet. And so we can put in we can do this data calculation just like in chapter 7. So we want it to be longer. So the probability that x is greater than 95. The probability that's longer than 95. So 95 is less than x, and we get 0.3190 when we round to 4 decimal places. Now, what is the probability that a random sample of 20 time intervals between eruptions has a mean longer? So the key words there are mean and sample size. So now, instead of doing the probability that x is greater than 95, we're going to do the probability that x bar is greater than 95. So when we change it to x bar, that changes the standard deviation. So I'll just put both of them in here at once. So the mean stays the same, remember, but the standard deviation becomes 21.25 divided by the square root of the sample size, in this case 20. And so you can see what that does to the graph compared to the original. It makes it, and let's, a lot narrower. In fact, quite significant amount narrower, right? This is the graph that's big here, and I'll change colors again so that they're not like the same color. The red one here is the new one. And notice how it's a lot narrower than the other one. Because now we're doing the mean of the mean of the means, and you expect means to be closer to the population than individual data points. So now we can answer the same question for this one. We want to know what's the probability that it's greater than 95. And notice 95 is still out in the same data place, but now it's a very narrow tail. That dark part at the bottom is the new curve we're looking at. And so that's 0.0177. 0.0177. So it's a lot less likely that you would get this unusual data value as a mean for a sample than it is to get an individual data value by itself. So what happens if we have a random sample of 30 time intervals? Okay, right? So that's the same thing, right? We can do stat, distribution plot, normal CDF, 85, 21.25 divided by the square root of 30. And notice that one is even narrower. So if I zoom in on that one, we get an even narrower graph. Okay, than the previous two. And so that leaves even less room in the tail. So when we go to do our CDF here, we should expect a value that's even smaller. And in this case, yeah, we get 0.050 if we round to 4 decimal places. So the probability here that x is greater than 95 is 0.0050. So what effect does increasing the sample size have on the probability? Well, it makes it go down because the mean is not included in our interval. So the probability decreases because the mean is not in our interval. And what might you conclude if a random sample of 30 time intervals between eruptions has a mean longer than 95 minutes? Well, there's a 0.5% chance of that happening. So that would mean this sample is unusual, and we might conclude the population mean, mu, is no longer 85 minutes. And this is the kind of thing we're building up to, is the idea of how can we use data values and probability to make conclusions about a population. And the way we do that is by doing this kind of probabilities. So why don't you all flip over to the next page and try doing these problems on page 5. Pause the video for a moment, run through these problems, and when you're ready, you can turn the video back on and we'll go through them together. Okay, So let's go ahead and run through these together. So we're talking about the length of a human pregnancy, and it's approximately 266 days with a standard deviation of 16 days. Also notice I didn't mention this on the last one, but we are approximately normally distributed. So that means it does not matter how big our sample size is. Okay, so let's go. I'm going to go ahead and start by getting rid of the normal distributions we just did, and we'll do a new normal distribution with a mean of 266 and a standard deviation of 16. And then we can zoom in on that by hitting the little magnifying glass just to the left of the question mark. And there's our new graph. So there's our new normal distribution. It looks a lot like all our other normal distributions, just located differently. So what would be the probability of getting a pregnancy that lasts than 260 days? So that's the probability that X is less than 260. So to do that, we can just put in our CDF, and we want X to be smaller than 260. So X is less than or equal to 260, and that's 0.3538. Now, if we decide to do the same thing, so first they ask us to describe the distribution sample. So because the population is normal, the sampling distribution is also normal. In this case, with a mean mu sub x bar of 266 and a standard deviation of 16 divided by the square root of our sample size, which is 20. So what is the probability that a mean is less than, is 260 days or less? So that's the probability that x bar is less than 260. Well, to get that, we have to change our standard deviation. It's no longer just 16, it's 16 divided by the square root of 20. Okay, and we get a much narrower graph, and so when we do that, we get a much lower probability, 0.0468. And what would you expect to have happened if we did it instead for a sample of size 50? Well, it should get even narrower, right? So we just want to change the sample size, so we just change what's under the square root, and we get an even taller graph that's much narrower, and the probability there is 0.0040. So what might you conclude if a random sample of 50 pregnancies resulted in a mean gestation period of 260 days or less? Well, you conclude that this is unusual, and therefore the population mean may have changed. And we've already kind of done an example like this, so I'm going to skip over this last page of our notes, and that's it for section 6.8.1.